Okay, let's continue from where we left off in last class. We were discussing communication complexity, and in particular, we kind of talked about a couple of problems, equality and disjointness, and various models of communication. And just to remind you, we were thinking of two parties in the communication setup. And a function which has two inputs. We want to compute it. The output of the function is very short, let's say. But the question is, how much do the two parties, say Alice and Bob, need to communicate about the inputs to be able to correctly compute the output, or compute it at least with probability 1 minus epsilon for every input. And we considered two different kind of random models where Alice and Bob have their own sort of private random bits, or maybe they share some randomness which is visible to both of them at the same time. Okay, yeah, before we go further, let me just let me just mention two very nice references that I forgot to kind of include last time, which is, there is a classic book by Gushilevitz and Nissan from 97, and there is a more recent book just from last year by Anup Rao and Amir Yahdayev. And the more recent one in particular includes some of the information theoretic stuff we'll talk about. These are both, very nice references, and I think the Rao Yahdayev book is available online for free in case you want to take a look. Okay. Now, just to continue our discussion, we sort of wanted to relate these two communication models where either Alice and Bob use their own randomness or they're allowed to share some randomness, and saw that shared randomness is definitely stronger, or sort of we need no more communication than private randomness, because of course they can just have a shared tape and Alice and Bob can just mark their portions and read that, and they don't read each other's part. So it's at least as powerful. And then we also claimed that it's not much more powerful. In particular, if you are kind of willing to change your error probability a little bit, then for an additional delta in the error probability and an additional log n in the communication, you can simulate a public coin protocol, or sort of something using public randomness with just using private randomness. And the idea was that if we know that there are only few possible random strings that are used in the public randomness, then, for example, Alice could just sample one of these strings using her private randomness, and if there are t strings, she can just send log t bits to Bob, so that Bob knows which of the t strings Alice sampled, and then it's known to both of them. Then they run their public randomness protocol. Okay. And I claimed last time that the fact that there are only few random strings that we need to work with is basically without loss of generality, at least if you're willing to suffer a little bit of error. And said that this should follow from Chernoff bound. Anybody try this? Any suggestions? Okay, so let's see what we are computing, right? So if you look at the public coin protocol, it samples some shared random string R and then computes, let's say we fix an input pair X and Y. Okay. So now this protocol computes whether so it computes some value of some guess for the function X comma Y, and the probability that it's let's say not equal to the correct answer is less than equal to epsilon. That's by assumption. That's our public coin protocol. And we can just think of this as some random variable defined on this probability space of random strings. It's a deterministic function of the string R. But as the string R is sampled randomly, this can be thought of as a random variable. So we just know that the expectation of a random variable is at most epsilon. And so we can, if we evaluate it on independent samples, the empirical average will be very close to the true average just by concentration bound. So in particular, if we look at and let's say we sample these randomly. Then this average is greater than equal to epsilon plus delta with probability at most some constant times delta square times t. That's just Chernoff bound. This is just a random variable which takes values in 0 or 1. So we can, the average of n independent samples is very close to the true average. And so if we choose t to be roughly some power of n over delta square should work. Then the probability that for this fixed x and y, this empirical average deviates too much from the true average is at most 2 to the minus 3n. So that means that there exists R1 to RT such that for all x and y, there are only 2 to the 2n choices for x and y. The empirical average of the protocol run with one of these random strings computes the wrong output. Well, there exists R1 to RT, or rather the probability over R1 or R1 to RT that this protocol computes gives higher probability is less than equal to n. So in particular, we can so by contrapositive, there is some choice of strings R1 to RT such that once we fix them, if we just run the protocol on one random string from this set, it gives the right answer with probability at least 1 minus epsilon minus delta. So the error probability is at most epsilon plus delta. And we just need about n over delta squared strings, which the log of which is log of n over delta, and then that's proved the claim. Okay. Any questions before we proceed? Just Chernoff. Sorry.
Question. So this is like not constructive, right?
This is not constructive. So
okay.
I'm just saying there is some protocol, but I'm not telling you how to efficiently construct a protocol.
Right. So then is there, I guess the natural question is there like a good way to efficiently construct such a protocol?
Mm, good point. Okay, so you have to say what you mean by, I mean, I guess you want a deterministic construction of such a protocol. Of course, randomly I mean, this is kind of randomness in the pre-processing, right? I'm just doing the randomness before before looking at the inputs. And if you allow me that, then the construction is also easy. I just fix a random choice of R1 to RT. But you want a deterministic construction, but for that, yeah, you might have to look at the code of the protocol. I'm not sure I can do this black box. Does that address the question?
Thanks.
Yeah.
Yeah.
Okay. Okay. Before we proceed, let me just make another simplifying assumption about the protocols. It's essentially without loss of generality. So we've kind of viewed protocol as these sort of trees where every node of the tree is labeled with either a function which kind of describes how sort of Alice will speak at this point or Bob will speak at this point. It will be convenient to sort of say that whether Alice or Bob is going to speak just depends on sort of not even on the previous history, but just kind of what time instant we are at. So if we are at time 1, Alice will speak, time 2, Bob will speak, and so on. Let's just fix this order in advance. And this is just kind of a natural thing to do. If I mean, the two of us were talking, but we had some sort of microphone which may be switched off after 1 second, switched on for the other person. And if someone else was saying something interesting, I would just sort of stop during my turn, not say anything. And then when their turn comes, let them continue. So, and that's basically what we do in the protocol. So if we have, at some point, it's Bob's turn to speak, but, or sorry, Alice's turn to speak according to the original protocol. And the blue nodes are where Alice is speaking, the green nodes are where Bob is speaking. I've not labeled all nodes. Then we can just sort of, now if we want this sort of to impose this rule that at time 2 Bob should speak, then we will just kind of let Bob speak, but then ignore what he says. So just make 2 copies of whatever was happening below that. So basically, irrespective of what Bob said, we will continue as if what Bob said did not matter, and then we will continue listening to Alice after that. So this is just going to at most double the depth of the tree. So the communication complexity grows at most by a factor of 2. So, and we will be kind of interested in the asymptotic communication complexity, and the constant in front won't really matter for us. So this is essentially without loss of generality, at least if we are interested in asymptotics. Any questions? Okay, this is just, yeah, slightly simplifies some of the inductive statements. We don't have to kind of always do case analysis of who is going to speak next. Just depending on if we are talking at a time instant which is odd or even, we just know who's going to speak. Okay. Now let me come to the kind of problem we will actually study or talk about today, which is the disjointness problem, which we introduced last time. It's just an AND of NANDs. So this is just saying that xi and yi are not both true together, so not AND. And as we saw, if you think of x and y as indicators of subsets of elements 1 to n, then this is just saying the subsets are disjoint. Okay. And yeah, this problem is kind of a canonical problem in communication complexity. It's there are lots of other problems which can be reduced to this, or which or like a lot of other settings where this problem is useful as a lower bound technique. So this has been fairly intense and sort of extensively studied. And One of the first lower bounds was due to, it has a history associated with the University of Chicago, but was due to Bavai, Frankel, and Simon from 86, who proved a square root n lower bound. And square root n is kind of a natural barrier for this problem. And later, using a somewhat different technique and a somewhat different model of randomness, or like randomized communication complexity, which is equivalent to, which can be proved to be equivalent to the one we are looking at. Kalyan Sundaram and Schnitger proved an optimal omega n bound, but the proof was complicated. It was somewhat simplified by Sasha Razborov in 90 using similar techniques. And a very different proof and conceptually much simpler proof was given by Bar Yosef, Jayakumar, Kumar, Shivakumar in 2004, which also was a paper that introduced a lot of information theoretic techniques in the area. The proof I will discuss is actually kind of an adapted version of a proof by Bowerman with some modifications due to me. But yeah, so hopefully that didn't introduce any errors. But these are both proofs which use information theoretic arguments, although somewhat different or slightly different arguments. And I'll kind of sketch the difference later. This problem continues to be studied, and even kind of if you are allowing error which is very close to half, just slightly better, then kind of a standard amplification argument will show that the previous bounds imply that the communication complexity should be at least epsilon square n. But the true answer turns out to be epsilon n, which was used for some lower bounds for linear programming for optimization problems. And this is due to Bowerman and Moitra. And there is also kind of a nice survey outlining some of the history, although not completely up to date, by Chattopadhyay and Pitasi, outlining some of the connections of this problem, various models where this is useful, and also different known bounds for this problem. Okay. Before we kind of prove the information theoretic bound, let me just quickly illustrate this issue of epsilon square n bound, or kind of reducing the error of a communication protocol. And it also says that the bound 1/3 in this all these results is kind of arbitrary. You can pick any constant, and it will just change the constant in the omega notation and won't really matter. So we can sort of prove the bound for our favorite constant here if we want. And going from, and let's just see how to go from error, say half minus epsilon, to error, say at most 1/10. And the idea is just kind of, if the algorithm is at least slightly correct, or it's there is at least some reasonable chance that it's correct, then if we run it many times and take majority, then hopefully at least we will have more than half of the kind of runs as giving the correct value. Okay. And in particular, it's the probability that the majority is incorrect is, again, the probability that we sampled k random coins. The probability of heads was half minus epsilon, but when we actually looked at the tosses, more than half of them came out heads. Coming up heads here is giving a wrong answer. And so we know that this is roughly some constant times epsilon square. And so this bound is less than equal to, let's say 1/10 for k, which is some constant over epsilon square. And so this gives us that, yeah, this is a calculation we have done a few times now, but this shows that if you want to look at error 1/10, and the communication complexity of getting error 1/10 is at most 1/epsilon square times the communication complexity of getting error half minus epsilon. And so if you prove lower bound on the 1/10 error complexity, you automatically get a lower bound on half minus epsilon. And likewise, you could replace this half minus epsilon by 1/3, and that will just give you some other constant here. And so you can relate different error probabilities to each other using just a simple amplification argument. And in particular, we'll work with 1/10 just because it's slightly convenient with the parameters. Any questions? Okay. Now let's get to the information theory part of this. So recall that a protocol, we were considering arbitrary inputs, X and Y, X given to Alice, Y given to Bob. And in general, we talked about protocols where there is kind of some public or shared randomness. There can also potentially be private randomness. And we saw that really, at least for the kind of bounds we are looking at, any one of these is enough, but it will be convenient to kind of keep both just because it will be easy to design protocols using both public and private randomness. It's just kind of more convenient for bookkeeping. We just, instead of saying that we are using public randomness, but here is the portion Alice is not allowed to look at, here's the portion Bob is not allowed to look at, we'll just call it private. And another thing is, if our protocol is correct on all inputs, then it's also correct with probability. Oh, sorry, this should be 1/10. If a protocol makes an error at most 1/10 on any given input, then in particular, when we sample inputs from a distribution mu, it still makes an error at most 1/10, no matter what distribution we use. And so in particular, to introduce information theory, we will use some distributions, but the bound we are going to state kind of holds true for all distributions, at least on the communication complexity. So suppose our inputs are sampled according to some distribution. We'll define the information cost of a protocol as basically how much does Alice learn from the interaction given what she already knows. And the same for Bob. So it's a mutual information of the interaction with the protocol where we will need to keep track of the public randomness, and I'll show in a minute that private randomness won't matter in this kind of expressions. So we're just going to use this symbol pi to denote sort of everything about the protocol that we are keeping track of, which is all the messages exchanged plus the public randomness. Okay. And yeah, as we'll see in a minute, private randomness won't matter. Okay. And we can just think of intuitively of this information cost as how much does sort of Alice learn given what she already knows, which is the input X, and similarly, how much does Bob learn given what he already knows. Okay. Any questions about the definition? Okay. And just to clarify, when I say mutual information, I have to specify a distribution on the random variables involved. So the inputs X and Y are sampled according to this distribution mu. So if you want, we can sort of write it this as in the mutual information according to the distribution mu, just to remind ourselves. But it's the notion of mutual information we have seen already. And the claim is that the communication complexity is lower bounded by the information cost, even for the worst distribution mu. So pick your favorite distribution, prove that the protocol has large information cost, that gives you a lower bound on communication complexity. Okay. The protocol we are assuming is such that on every single input, it computes the output correctly with probability at least 9/10. It makes an error with probability 1/10. Okay. Any questions before we proceed? Okay. And let's check this bound. So the information cost has two terms. So let's just check for each term. So the mutual information of, let's say, pi and x given y. So let's actually break it down into these two parts, which is the messages exchanged and the public randomness. And then we can use chain rule. I claim this term is 0. So instead of putting the public randomness in the kind of part together with x, we could have also thrown it in the conditioning. Because the randomness is independent of both x and y. It doesn't depend on the input at all. It's just sampled independently, and then Alice and Bob use it to do whatever computation they want. So randomness and x are independent given y. It is actually independent from the tuple x comma y jointly. And what remains, the mutual information of the messages with x conditioned on something is at most the entropy of the messages exchanged, which is at most the expected length of the message written down. Like, so if you are looking at n-bit strings, the entropy can be at most n. And this is at most the maximum length of any messages exchanged by the protocol, which is how we define the communication complexity of the protocol. So, and the communication cost of the protocol. So for any protocol and for any distribution mu, the information cost is a lower bound on the communication of the protocol, or communication cost or complexity of the protocol. And I mean, yeah, up to this factor of 2, which comes from considering two terms. Okay. Any questions?
So Madhur, here would it be right to say that for the equalities to hold, the distribution would be like just centered on the worst case input, these xy, and just supported on that?
Well,
or no?
That's not enough, because I mean, the entropy of M will be maximal if not just that the distribution is on the worst case input or the kind of there, but M actually is uniform over all strings of the maximum length that can happen. And that, yeah, I can't think of a case in which that will happen. That is an upper bound, but it's potentially a strong upper bound. Right?
So you're saying that it might happen that this never hold, the equality doesn't hold.
Well, you can come close to it within constant factors, and that's enough for the kind of things that we are talking about. But I'm saying there are many sources of randomness. Just A, it comes from the worst input. Worst can be, of course, I mean, in the terms of error probability and communication length, but I'm guessing you're saying communication length. Then there is kind of all these randomness, the private randomness of Alice Bob, the public randomness, which is shared, which will also change the length of the communication. So the worst input still is the one where the expected length of communication is worst according to all this randomness potentially. And we are actually interested in the entropy of the messages, not the length of the messages. So the entropy will be equal to the length of this worst input if the input is kind of essentially uniform, the transcript or the messages are uniform over their length. And that's, in general, sort of an exact equality is unlikely to hold, or I don't think I can find an example except for maybe esoteric problems. What might happen is that the worst length is, or maybe the tree is kind of balanced. So all inputs roughly give you about somewhere between n over 2 and n as the worst case communication. And the entropy is such that the entropy is kind of maybe at least n over 4. So you will get something which is maybe some constant times the worst length, but not quite the worst possible length in the protocol.
Right. Okay. Yeah. I get it.
Yeah. But I mean, yeah, because we are not worried about asymptotic issues, we might as well just use this crude bound. I mean, you can come within constant factors of this one. And that might happen for a lot of inputs. Like there can be, your problem can be such that essentially all inputs require the same kind of communication. And in particular, for disjointness, you can construct distributions where, I mean, it depends on the protocol, but for a given protocol, I can probably find distributions where there are essentially 2 to the omega n possible inputs, which will all require a lot of communication. Okay? But this omega is important. There will be some constant. Does that make sense?
Yeah.
Okay. All right. So I have to say that this is this definition of information cost is kind of a more recent one due to Braverman and a paper of Barak Braverman et al. Before that, and I'll mention the history. This is slightly different from the 2004 proof of Bar Yosef, and I'll mention their definition later, maybe once we can see this proof in full. Okay. Just might be a useful exercise to see that the private randomness doesn't really matter. So even if we included, the mutual information will not change. And so we defined the information cost without talking about the private randomness. And for example, I mean, the private randomness should be included in the conditioning, because if you think of what Bob knows, Bob actually knows Y and R sub B, which is the private randomness of Bob. But I claim that doesn't really change the definition. So is the statement clear before we prove it? And this is where this kind of assumptions about the structure of the protocol or this kind of inductive style will be useful. So let's prove it by induction. Let's write the communication as before. We can only keep the messages here and put the public randomness in the conditioning, just like the previous computation, because it doesn't depend on X and Y. And we'll get to the private one in a bit. And just by chain rule, I can write it as, let's say, the communication up to the point 2t plus the bit spoken at time 2t plus 1 plus the bit spoken at time 2t plus 2. And I'll kind of use induction to handle the first term. Yeah, this is why I don't like writing M and R both, because there's already too many things to condition on. But this is the one time we will need to do it. Okay, similarly, the right-hand side we can write as now include the public randomness, and we get the same kind of terms. Okay. Now, these terms we will just claim by induction that they are equal. And we will start the induction at t equals 0. So the base step also we will just prove right now in the proof of the inductive step. But if we are at t greater than 0, then we will just claim that this is true by induction. I claim that the last terms are actually not a problem. So recall that we've kind of set the convention that at odd time instants, Alice speaks, and at even time instants, Bob speaks. Okay. So this is something, it is a time instant where Bob speaks, and what Bob says is a function of the input that Bob has, the public randomness, the private randomness of Bob, and the previous communication. So it's a function which is completely determined. So the entropy of M2T plus 2 is actually 0, conditioned on what we have so far. So this mutual information term is 0. The same is actually true for the last term here, because now it's not completely determined, but it's independent of x, because it's still a function of y r sub b and the previous communication. And given the previous communication, it's independent of x. So the last terms in both of these are 0. And now we come down to analyzing this one term that remains, and we just need to prove that those terms are equal. And that will give us what we want. Okay. Any questions? Okay. And it requires a little bit of rearrangement, but can use the simple sort of identity, which I think Gautam also used in one of the discussion sections. But basically, that the mutual information, how much does it change when we condition on additional stuff? So, and you can kind of write it slightly differently. I mean, nothing deep, just observe that the terms marked in red and the terms marked in green just add up to the same thing. They both add up to the mutual information of A and BD conditioned on C. This is just chain rule applied in two different ways. Okay. And this can be used to kind of conveniently rearrange the two terms that we have. So we want to understand now this term and this term. And we can write the difference similarly. So in particular, yeah, this kind of using this R sub B as the additional conditioning, we can write the difference now as And again, just because it's Alice's turn to speak, what Alice is going to say is a function of Alice's input and is in particular independent of Bob's randomness given the history of the communication. So both these terms are also 0. Right. It's a little bit of rearrangement, a bit too many kind of variables to condition on, so requires a little more kind of careful thought, but it's not something very involved. Okay. Any questions before we proceed? This is just to justify that we didn't include private randomness in the cost, but yeah, it's basically free in the information cost. Okay. Now let's get to the kind of more interesting part of the proof. So we will be able to show that the information cost of a protocol computing disjointness is essentially n times the information cost of a protocol which is computing a function of 2 input bits. That they are the not and function, or the fact that they are not both 1 simultaneously. Okay. And we'll show that in particular for this distribution where the true answer is actually always 0. So this is a distribution where, but the protocol is supposed to be correct on every input, not just on this distribution, remember. We'll just analyze the information cost on this distribution, and we'll show that the information cost of the protocol for disjointness will be at most, or will be at least n times the protocol for 2-bit inputs, which computes NAND with probability at least 9/10 on every input. And then we'll show that the information cost of any such protocol for 2-bit inputs should be at least some delta, which will be a small constant, 1/1000 or 1/10,000 or something. And that will imply that the information cost of the protocol for disjointness is lower bounded by n times some constant, so omega of n. Any questions about the 2 steps that I kind of outlined here? We'll get to each of them and then prove each of them. Okay, and this is roughly the reason why information theoretic proofs are quite useful. Because of various kinds of chain rules, they often allow reducing the analysis to a small problem, often on 2 bits. This is basically the same idea that is used in a lot of information theoretic applications, like parallel repetition and parallel repetition of games, or 2-player games, of various other kind of communication complexity lower bounds. The same thing is also used in some information theoretic applications in metric geometry. All of them, it's kind of some chain rule, then the analysis of some fixed constant size object. And also the kind of both these steps are somewhat generic in terms of how they are done. So I'll say that in a minute. But chain rule is the key thing. Okay. So now let's get to the reduction step, which is done by what's called simulation. So we'll kind of prove this in the contrapositive. We'll say that given a protocol for disjointness, I will come up with a protocol pi hat for computing a 2-bit NAND on inputs x hat and y hat. And sorry for the bar over hat, but such that the information cost is 1 over is at most 1 over n times that of pi. Okay. So in particular, I will give you a protocol which works with probability at least 9/10, has information cost 1 over n times that of pi. So the best protocol can only have lower cost, and so that will prove the claim that the cost of pi is at least n times that of the best protocol for NAND. Okay. And this kind of reduction will be by simulation, that we have kind of 2 inputs x hat and 1 hat, both of them are just 1 bit. We will sort of create n-bit inputs out of them, x and y, and just feed them to the protocol for computing disjointness. And we will say that we are kind of create these inputs x and y in such a way that we don't reveal too much information about x hat and y hat. In particular, the information revealed is 1 over n times the information the disjointness protocol reveals about its big inputs. And to do that, we will kind of pick a random location between 1 and n and write x hat and y hat in that location, and then fill in all the other locations kind of ourselves, or Alice and Bob will fill those in. And once so now they have kind of n-bit inputs x and y, and they'll run the protocol pi on these. And it kind of, it seems a little weird the first time, like there's something which is sampled with public randomness, something with private randomness, but this is, you kind of see this makes some of the computations more convenient. And let me say that, I mean, the proof of Bar-Yosef et al. Is slightly different. The reason I wanted to do this proof is to basically show this simulation, which is the same one used in a lot of proofs using this kind of chain rule based arguments. And here, whatever is written in blue is sampled using public randomness. So in particular, are the random index t where we put x hat and y hat. And all the x values for indices less than t and all the y values for indices greater than t are sampled using public randomness. And when I say an x value is sampled, it's sampled according to mu. So mu gives us a joint distribution on x and y. So in particular, I look at the marginal for x, which is 0 with probability 2/3, 1 with probability 1/3. So I just sample x to be 0 with probability 2/3, 1 with probability 1/3. Okay. And same for the y values. We can sample them using public randomness. And then Alice and Bob kind of complete the rest of the parts for their inputs. So Alice is supposed to have x, so she fills in the rest of the entries of x, such that the joint distribution of this part is mu. So the value of y has been filled in by public randomness, so she can sample the value of x conditioned on the value of y, and so the joint distribution is mu. Same for Bob, kind of fills in the remaining entries of the string y. That gives n-bit inputs x and y, and then once they have them, they can run the protocol pi, capital pi on this. Okay. Is the definition of the description of the simulation okay? What parts are computed by whom? What are they trying to do? Okay. So now I claim that the information cost of this protocol pi hat is 1 over n times the information cost of the original protocol. And okay, by the way, because we chose mu in such a way that in each of the other columns, except for x hat, y hat, you have at most one of the entries equal to 1, and sort of at least one of the entries is equal to 0. So it's kind of designed in a way that the disjointness, or like x and y are disjoint if and only if x hat and y hat are not both simultaneously 1. So if pi computes this correctly, with probability 9 over 10, then it also computes the NAND of x hat and y hat correctly with probability 9 over 10 for every input x hat and y hat. Okay. So this is a protocol which works with probability 9/10 for these kind of 2-bit question of NAND of x hat and y, okay, on every input. It just so happens that we are using the distribution mu, but the protocol constructed here for x hat and y hat works on every x hat, y hat. Okay. Once we have the kind of protocol in place, the analysis of the information cost is actually not that complicated. And it's just a matter of kind of writing down the expressions and just kind of mostly following your nose in the analysis. So the information cost was supposed to include all the public randomness and all the messages. So let's include, so the public randomness of pi hat is whatever we sampled and is indicated in the color blue here, which is the entries of x, the entries of y, and the index t, where so I'm in denoting these the capital T because I'm thinking of it as a random variable now rather than number. And then whatever randomness and messages pi exchanges. So everything that pi does is also part of the information cost. And we are looking at the mutual information this between this and y hat, let's say. Given x hat, there will be a symmetric term which will have sort of mutual information with x hat given y. Okay. As before, we can kind of push the public randomness in the conditioning. And the 1 over n comes basically by kind of expanding the conditioning over capital T. So mutual information conditioned on capital T just means that we look at all values of capital T. Let me just collect the other stuff here. And now conditioning on this value of capital T just means that I replace y hat by the tth bit of a big string y. Same here. All right. Here I am using the fact that if I look at x that is sampled from mu to the n and y is sampled from mu to the n. So the marginal of any coordinate looks like x hat, y hat. Oh, sorry, x, y jointly is sampled from mu. And because private randomness is free here, we can actually add that. So in particular, we can add the private randomness. Oh, did I make a mistake? No. We can add the private randomness of Alice for free. And then I can just kind of combine all the x terms. I have all the bits of x. I'll just call that the entire string x. And this is nothing but the chain rule applied to mutual information of pi and y. So I get 1 over n times the mutual information of. Okay. Similarly for the other term. So we will just get that the information cost of this protocol is 1 over n times the information cost of the protocol for disjointness. Basically, because we hit the input in 1 over n, sort of 1 of n random locations. So we expect that doesn't reveal more than sort of 1 over n times the cost it reveals about the entire string, except that kind of making this precise requires this sort of quite clever idea of sampling in these kind of public and private phases, the inputs of x and y. Okay. Any questions? Okay, that's the most kind of important part of the proof. Basically, the sampling process, and once you do this computation, I mean, yeah, again, it involves a few symbols, but this is very straightforward. There is nothing it's kind of unusual in each of these steps. And then it reduces the question to just kind of understanding this protocol for this 2-bit function NAND, and that part is kind of mostly mechanical. So once you have that, it's a question of for a 2-bit function, can you say that you need at least some constant amount of information to actually be able to compute that function? Although it requires a little bit of work, because the protocol pi is still arbitrary. So we are trying to say there is a protocol, let's say pi hat, which is computing this NAND function and is going to exchange at least information which is about 1 over 1,000. And as we saw in the simulation, the protocols could be can be very complicated, even if it's trying to compute a very simple function. And we have to say that all these very complicated protocols will also not be able to sort of compute the NAND without revealing at least some information. And to do that, yeah, I mean, there's one nice argument, but before we go there, let me just kind of drop all the hats and just sort of think of protocol pi on inputs x and y. Now both are 1-bit input each, and I'm just trying to compute NAND with error at most 1/10. And I claim that the amount of information exchanged must be at least some small delta. And I'll prove it by contrapositive. But any questions before we proceed about the setup now? Now we're just kind of down to analyzing a function on 2 1-bit inputs. And the n is kind of gone. But note that the protocols could still be arbitrarily long. And this was actually one bottleneck in previous analysis on communication complexity, that it was possible to prove bounds for protocols which were maybe had sort of 2 rounds of interaction or 3 rounds of interaction, but the fact that the protocols could be arbitrarily long was an issue in the analysis. And the nice thing about information theoretic methods is that it really doesn't care how long the protocol itself is. It could be arbitrarily complicated. It just measures somehow how much information the protocol reveals. Okay. And we'll do this in 2 steps. Again, where we will say that if the information revealed by the protocol is small, then it means that, okay, before that, a little bit of notation. So let's say Pxy is the distribution on whatever the protocol writes down, or the transcripts of the protocol. So this is again randomness, public randomness, and the messages exchanged by the protocol. And sorry. So what the protocol writes down is potentially a very long and very complicated string, but whatever it writes down, we're just kind of going to look at this distribution over these long strings and just call that Pxy, which depends on the input X and Y. So if X is 0, Y is 0, then we have one distribution, which still depends on all kinds of sort of randomness, and potentially there's also private randomness. So it's still some involved distribution, but the inputs are now fixed because they're only 1-bit inputs. We can just consider 4 cases, 0, 0, 0, 1, etc. Okay. And the fact that the protocol computes the function correctly, and the function is kind of NAND here, means that the distribution for 1, 1, where the right answer is where the right answer is 1, if the inputs are both 1, and the right answer is 0, sorry. And for 1, 0, where the right answer is 1, because sort of you have not and. These two distributions should be far apart. And this is again, there is in particular on these two distributions, which give you complicated outputs, maybe this entire transcript of the protocol. But if you look at the last bit in the protocol, that tells you the correct answer. And the distribution of the very last bit is different in these two cases. It's either 1 with higher probability or 0 with higher probability. So in particular, these two distributions have some L1 distance or statistical distance. The same is true for also 0, 0. Basically, all the other 3 distributions are far from 1, 1, because the answer is different from 1, 1 than all the other cases. And we'll prove the first inequality will say that if the protocol has low information cost, in particular smaller than a constant, so let's say smaller than some delta, then the kind of 3 distributions where the answer is 1, or like the 0, 0, 0, 1 and 1, 0 are all very close to each other. And so in particular, you have that these 3 distributions have to be kind of close to each other. And we know that all 3 of them have to be far from the 1, 1 distribution also. So you kind of have this lollipop diagram. But then the next inequality says that actually that's not possible. So you cannot have delta to be too small. And this in particular says that the 0, 0 and 1, 1 points cannot be too far apart if the others are close. Okay. So this will give us some upper bound, or sorry, some lower bound on delta in particular, and any constant is fine for our purposes. Okay. Any questions about the statements of these results before we proceed? Okay. Notice that this is still non-trivial because the protocol is arbitrary and the inputs maybe are very simple, X and Y, but the protocol itself can do can continue for whatever amount of time and can exchange as long messages as it wants to. Okay. Just to compute what the information cost is, let's just look at it one term at a time again. So let's look at the mutual information between the protocol and X, let's say, given Y is equal to 0. And remember, these 2 inputs are now sampled either 0, 0, 0, 1, or 1, 0 with probability 1/3 each. That's the so yeah, I'm kind of expanding the conditioning step. So with probability 2/3 Y is 0, and with probability 1/3 Y is 1. when y is 1, x has to be 0. So there is no entropy in this term. So in particular, doesn't contribute anything. And then we kind of use a computation from one of the homeworks that the mutual information of A and B can be written as the joint probability log of joint probability times the product distribution. This is something you saw in homework 1, and in fact, more kind of nuanced version is that you sample A, and then what we are left with is the KL divergence of the distribution on the sample B, distribution on the first input versus the marginal on the first input. So this was an expression which was one of the problems in homework 1, or was used in one of the problems in homework 1. Okay. And using this, we can write down the mutual information between pi and x. Given that y is equal to 0, x is 0 with probability half and 1 with probability half, conditioned on y equals 0. So we get two KL divergence expressions, each with probability half. And when we plug in x equals 0, the distribution of pi becomes p0, 0, because we've already set y to 0. And the marginal, when we haven't plugged in the value of x, is p0, 0 plus p1, 0 divided by 2. Same for the second part. This is nothing but the Jensen-Shannon divergence of 0, 0 and 1, 0, which again we know is greater than equal to 1 over 8 ln2 times the L1 distance between the two distributions. And this was a problem in homework 2. And yeah, basically you plug in a similar bound for both expressions. That gives the right hand side, which gives the distance between 0, 0 and 0, 1 and 0, 0 and 1, 0. Okay. Any questions? So this part is mostly kind of direct computation or sort of cases based on the 4 inputs. But yeah, we still have to do some work because pi can be weird. The next part again is, and there are many different ways of proving these two pieces. This is just one possible argument that I'm showing because we've kind of seen some of the objects known here. The second part actually uses a special property or uses the fact that these are not arbitrary distributions, but they are coming from protocols. So in particular, it says that we are able to write down the probabilities as sort of some function which depends only on x times some function which depends only on y. And this is because, well, let's write down the probability of the message and the public randomness. And we can write it as the probability of the public randomness times the probability that the first bit of the message is spoken by Alice, given Alice's input and, well, the public randomness, times the second bit of the message is spoken by Bob, given the first bit of the communication times Bob's input and the public randomness. Okay. So this probability depends on the private randomness potentially, but the public randomness we can condition on. Then the next term is again, third bit is spoken by Alice, given Alice's input, randomness, and what has been said so far, and so on and so forth. So you can notice that alternate terms depend on X, and other terms depend on Y, but there is no term which depends on both X and Y, which is a kind of fairly useful property, and it crucially uses the fact that we have protocols. Alternating is just for convenience, otherwise it would look somewhat different, the factorization, but you would still have this property. And so in particular, if we know the randomness and the messages, we can just kind of write down as a product of the X part and Y part. And this gives a very nice expression, which is a relation between these two cases. Because in both cases, you will get F0 pi times F1 pi times G0 pi times G1 pi. So, and once you kind of are at this point, there are many ways to actually complete the proof and prove the above bound. In particular, yeah, I mean, this is sometimes referred to as the cut and paste property or the cut and paste lemma for protocol. It kind of just says that the probabilities in these two inputs, if you exchange one bit, the product remains the same. Or, I mean, it's actually stated in terms of distances of a slightly weird distance called the Hellinger distance. But I mean, it's a kind of implies the following, which is if you look at summation square root p0, which is just like L1 distance. This is a kind of L2 distance between distributions, a particular one called the Hellinger distance. And then there are, and if you can basically prove by Cauchy-Schwarz standard ways of relating it to known distances. So basically an application of Cauchy-Schwarz can say that if you look at this sort of L2 distance, then it's related to the standard L1 distance between distributions that we saw on both sides. So this is just I wrote, can be just written in shorthand as P00 square root P1 1 and 2 square. And once you kind of plug in bounds from in terms of relating L2 and L1 distances, you get the statement of the lemma. Okay. That's, yeah, this is just something called the Hellinger distance, or this is this is the square of the Hellinger distance. So this is another distance between distributions. It's particularly convenient when handling some sort of distributions coming from vector spaces or inner products, just like the one we got here can be thought of as an inner product question. And so there are many applications where Hellinger is a bit more convenient to work with than L1 distance. But this part again is mechanical. It's mostly some simple computations related to distributions. Okay, let me not worry about kind of showing how to use it, unless how to use these disjointness bounds for streaming, unless someone wants to see it. But let me make a couple of comments about what we saw. So the definition used by Bar-Yosef et al. was slightly different. So in particular, they used, instead of saying, given what Alice knows, what does she learn about Bob's input, and same term for Bob, the definition there was just how much does the protocol reveal about both inputs X and Y. And this is sometimes, or maybe this is now referred to as the external information cost of the protocol, or how much does an outsider or an external observer learn just looking at the protocol, versus how much do Alice and Bob learn about each other. And it's a good exercise to check that the external cost is at least as large as the cost we talked about, which is called, just to distinguish, is referred to as the internal information cost. And this was kind of made explicit in this paper of Barak, Braverman, Chen, Rao, and also sort of discussed in paper of Braverman. In general, the simulation shows that we can always say that the information cost of computing k copies of a function is at least k times the information cost of computing one copy of the function. The same kind of simulation argument proves this. And it's open to say if this can be done for communication rather than information cost. So how faithful is this measure of information cost? And in particular, it's known that the error needs to change in communication complexity when we try to prove such a bound. The best that is known is a root k, and it's kind of an open problem to go beyond it. It's plausible that we might be able to even prove k over log k based on what is known so far, but root k is the best actual proof. Okay. Let me stop there, and next time I'll talk about Lowash local lemma. So this is just one sort of application of information in the communication complexity context that I wanted to mention. Next time we'll talk about a different application in DCS. Any questions?